This is the next step in the theory of the consumer. We're going to do basically the same thing that we did with the indifference curve analysis, but now we're going to do it with equations. We're going to do what's called the Lagrangian approach. We're going to look at the Lagrangian multipliers and try and come up with an optimization for the consumer given the constraints that they face. So now basically what we're doing is we're taking the indifference curves, we're turning them into equation form, and then we're solving for that problem. So we have a constrained optimization problem here. We have an equation that gives us the consumer's preferences, an equation that represents the constraints, and then we're optimizing within that scenario. So to understand the Lagrangian point, you have to look in you can look in your textbook for the section on the Lagrangian optimization or the utility function approach to consumer theory. In a lot of textbooks it's in an appendix. In Frank textbook it's in the appendix to chapter 3. In the Goolsbee-Levitt book it's in an appendix to chapter 4. This all depends on the editions, but all intermediate micro textbooks essentially go through this practice. And then once you move on to a class like Math Econ or graduate school intermediate or microeconomics, you will see Lagrangian analysis again, and then other things that branch off of this approach. This is a very common practice within advanced microeconomics to represent things in equations to try and make some things more precise and clear to illuminate some economic behavior. What I have done is I've given you basically a 7-step approach if you want a little cheat sheet or way to remember how to do the Lagrangian approach. So we have a 7-step approach here. These are the 7 steps in front of you. So this is the Lagrangian multipliers approach to constrained optimization. First, you're going to set up your equation and have a budget constraint. Next, you're going to get the first order condition for each variable, and then the Lagrangian. Basically, you're going to end up doing partial derivatives here for each variable, and then the Lagrangian multiplier. Third, you're going to solve each variable for the Lagrangian multiplier. Fourth, you're going to divide the first variable's first order condition by the second variable's first order condition. Fifth, you're going to solve for one of the variables. Sixth, you take that solution from step 5, you put it back into the first order condition of the Lagrangian, and then you should get an answer there. And then seventh, you put that answer back into the first order condition of the Lagrangian, and then you get the other answer. And then you figure out how the consumer maximizes their consumption. Okay, so what does all that mean? What do all the steps mean if we're going through this? Well, first off, you can see here we have a utility function. Generally, utility functions are something that is going to be given to you. There's some trickier problems that can be done where you have to basically figure them out from some other statement. But in this class, what we're going to stick to is you're given a utility function, and here it is. This is the utility, the way that the consumer gets utility. In this case, the consumer gets utility from a multiplicative relationship between x and y. So utility, or u, is equal to x multiplied by y. The next step is going to be figuring out essentially your budget constraint. Here sometimes you have to do a little bit figuring out, but basically it comes down to this. If we have 2 goods, if you think about it, the price of the first good multiplied by how many of that good you get, plus the price of the second good multiplied by how many of that good you get, needs to equal the amount of money that you have, or the budget constraint you have for those goods. So in this instance, let's say I have $40. If I have $40, well, what is my budget constraint equation going to look like? If I have a couple of goods to choose between, say good X and good Y, what I need to do is have basically 40 be equal to the price of X multiplied by how many X I get, plus the price of Y multiplied by how many Y I consume, and that will be my budget constraint. So M here is given in this equation as the total income. And then you can see P of X is the price of X, X is the quantity of good X, and then P subscript y would be the price of y, and then y would be the quantity of y. So in this case, if the price of y was 2 and the price of x is 4, and then your total income is 40, you would have 4x plus 2y equals 40 as your budget constraint equation. So now what we can do is basically head into step 1 of the Lagrangian multipliers approach. This first step is set up your equation with the budget constraint. So our budget constraint, we said, is this 4x plus 2y equals 40, which we got from the assumptions on the last screen. We also got from the assumptions on the last screen that our utility function was xy. So how you set up your Lagrangian equation is you have the Lagrangian is equal to the utility function minus the Lagrangian multiplier multiplied by, and in parentheses, your budget constraint. So in this case, we have the Lagrangian is equal to the utility function xy minus the Lagrangian multiplier multiplied by, in parentheses, the budget constraint. So in this case, that budget constraint is 4x plus 2y minus 40. Now, you might not get where the minus 40 came from, because if you look at the budget constraint, we have 4x plus 2y equals 40. Well, to plug that into the equation, what we have to do is we have to set that equal to 0. We have to zero basically everything out for a constrained optimization problem here. So what you could do if you look at that 4x plus 2y equals 40 is you can just subtract 40 from both sides, and you get 4x plus 2y minus 40 equals 0. And that's what actually gets plugged into that Lagrangian equation. So our final Lagrangian equation for step 1 is the utility curve minus the Lagrangian multiplier multiplied by, in parentheses, the budget constraint. And so it should be the Lagrangian is equal to xy minus the Lagrangian multiplier, and in parentheses, 4x plus 2y minus 40. Now, here's where your calculus has to come in. Step 2 is getting the first order condition for each variable and then the Lagrangian multiplier. So what you have to do is you have to look at your Lagrangian setup from the equation that was given to you, and you have to take the derivatives. So here we have to take basically what's called a partial derivative with respect to x on the equation, a partial derivative with respect to y, and then a partial derivative with respect to lambda, or the Lagrangian multiplier in this case. If you go through and you know how to do your basic calculus here, you can see the derivative with respect to x should churn out a situation that is just y minus 4 lambda. Now at the end of the equation, you have to really keep in mind and be careful with the positives and the negatives, because if you see, the entire equation is set up to be minus lambda multiplied by the budget constraint. And so that minus gets carried through to all of the different segments of that budget constraint. So you have to be really careful there with the positives and negatives. But here, you can work through the problem, make sure you know how to do your calculus. If you have questions with the basics of taking a derivative, you can come and see me or look online. There's plenty of resources that can show you the level of calculus that we're going to do in this class. But you should get the y minus 4 lambda when you take it with respect to x. And then when you take the derivative, the partial derivative with respect to y, you should get x minus 2 lambda. And then if you do a first order condition with respect to the Lagrangian multiplier, you should get basically what's in the budget constraint there, a 40 minus 4x minus 2y. And now we're on to step 3. Step 3 is going to be to solve each variable for the Lagrangian multiplier for the lambda. And what you want to do is basically you have 3 equations that you've solved for so far. You've solved for x with a partial derivative, you've solved for y with a partial derivative, and then you've basically done the budget constraint. You solved for the lambda. The lambda is kind of a separate issue, but what we're going to do right here is basically solve each variable, the x and y, and set them equal to that lambda. So far we had that y minus 4 lambda. what you're going to do again is basically have that equaled out to 0. You're going to 0 it out. So you have y minus 4 lambda is equal to 0. And then just solve that for lambda so we can do more mathematics with that equation, because we're going to get the other one also set up to the lambda. So first things first, you do the first equation where we took the partial derivative with respect to x, and you had the y minus 4 lambda that set equal to 0. You solve for lambda, and you should get lambda is equal to y over 4. And then you do the second set of equations where we took the partial derivative with respect to y, and you get the x minus 2 lambda, set that equal to 0. And then what you can do is you can solve for lambda, and you should get a lambda is equal to x over 2. Make sure you're actually working through the math in front of you so you can do the actual calculus, as that's going to matter a great deal. Here what I'm trying to do is just show you the steps as to how you approach the Lagrangian multiplier problems. Step 4 matters a little bit more and more complex Lagrangian multiplier problems. Here it's going to be quite simple. You just divide the first variable's first order condition by the second variable's first order condition when they're set up equal to lambda. And so what we're basically going to do here is cancel out those lambdas that ended up in both of our equations. So the first one, we had lambda is equal to y over 4. We're going to divide that by lambda is equal to x over 2. And we're going to divide those out, and then we can solve from there. So here in step 5, we're basically going to solve for one of these variables. There's a number of different ways you could do the math here. You could move this x divided by 2 variable over to the other side of the equation to get x over 2 is equal to y over 4 and cross multiply, and you get the same math. Here what I've done is I've basically just multiplied by the inverse of the x over 2, so I still have 1 is equal to y over 4 multiplied by 2 over x. As long as you're sticking to the proper rules of algebra, you're fine. And then we could reduce this situation down to 1 is equal to 2y over 4x, or 4x is equal to 2y. Once you have 4x equals 2y, you need to solve for one of these variables. Here we're going to pick, doesn't matter which one you do, but here we're going to pick to solve for y. So we divide out the 2 from the y, and that gives us 2x is equal to y. Now here, when we get to step 6, what we're going to do is we're going to bring back in that partial derivative of the Lagrangian multiplier, that partial derivative with respect to lambda that we took, the partial derivative that related to that budget constraint. We're going to bring that equation back in. So in step number 2, we got the first order condition for each of the variables, x, y, or with respect to x and then y, and then with respect to that lambda. Now we're bringing that equation back in, the one that we took where we had it with respect to lambda. We had an answer of 40 minus 4x minus 2y as our partial derivative with respect to lambda. We're bringing that back in, and what we're going to do is we're going to take our solution from the last slide, y is equal to 2x, and we're going to plug that into our budget constraint derivative here, and we're going to have 40 minus 4x minus 2y, but that now it is minus 2 multiplied by 2x because we're plugging y is equal to 2x in. So we have 40 minus 4x minus 2 multiplied by 2x. Again, this is all zeroed out in this constrained optimization format. And then from there, it's basic algebra we can solve. So we have 40 minus 4x is equal to 0. And then you can say, bring the minus 4x and minus 4x over to the other side of the equation, and you have 40 is equal to 8x. Divide out by 8, and you should get x is equal to 5. Here in step 7, put your answers back into the first order condition of the lambda. Basically, we're doing the same thing that we just did in step 6, but we're doing it with the other variable. So now we have an answer for the constrained optimization of the x variable, and we're going to put that back into this budget constraint partial derivative here. So our partial derivative of the lambda variable is 40 minus 4x minus 2y is equal to 0, and we have an answer now of x equals 5 being our optimization. So we're going to take that x equals 5 and plug it into that 4x, So now what we get is 40 minus 4 multiplied by 5 minus 2y equals 0. And we can solve now for y. So what we can do is we have 40 minus 20 in this situation right here is going to end up equaling 20 minus 2y equals 0. And then what you can do is take the y's over to the other side of the equation and divide by 2, and you end up with y is equal to 10. So y equals 10 in this constrained optimization from our first example. So what we can say with this Lagrangian approach is that given the preferences, the utility function of the individual, and given the budget constraint and the prices of the goods x and y in this situation, the utility maximizing bundle to the consumer is going to be 5 units of x and 10 units of y. So we've used our budget up, and if we're maximizing the utility from the different goods that we have coming in, given the indifference curve or set of preferences or the utility function basically that we have been given, this is our utility maximizing bundle of goods. 5 of x, 10 of y. Okay, so here's another example. This one's going to have a little wrinkle at the start. We're going to follow basically the same steps of the Lagrangian multipliers approach, especially for question B of example 2. But here's the situation. Carl is stranded in the forest and must survive on coconuts and quail. His utility function for those items is u is equal to 10c minus c squared plus 4q minus q squared. The two questions ask us, if Carl maximizes his utility and has no constraints on how many he can get, what will he do? So how many quail, how many coconuts? Coconuts are C, quail, Q. Part B, if Carl is able to get only some combination of 5 coconuts and quail, and they're equally hard to get, that's going to be your clue for the price, how many will he get of each if he is doing the best he can? Now, in Part A, this is going to be a little bit of a different type of question than what we're doing, but it's going to highlight the setup of a Lagrangian approach. Here in Part A, there is no price. There's plenty of quail and coconuts to go around, and you can get them basically without cost. There is no budget constraint. So we don't have that second part of the process that we had in the Lagrangian approach as I showed you the 7-step process. Basically, there is no budget constraint to optimize with here. So what we can do is we can just take the derivative of the utility function with respect to each commodity, the C and the Q, each variable, and set it equal to 0 to get our optimization here. There's no budget constraint, so we can do the optimization with the derivatives without any use of the Lagrangian because we have no budget constraint here. So our utility function again was this u is equal to 10c minus c squared plus 4q minus q squared. What we're going to do is we're going to take that utility function, we're going to take the derivative, the partial derivative with respect to c, the partial derivative with respect to q, get those first order conditions, and we can optimize. So here, if we do the first order condition with respect to c, you end up with 10 minus 2c. And then if you do the same thing to the original utility function here, but with respect to q, you end up with a solution of 4 minus 2q. You can set those equations equal to 0. Here, the 10 minus 2c is equal to 0. We can solve for that, and we've optimized, without a budget constraint, the best, the max bundle of C for this consumer. So in this case, 10 minus 2c, you can solve, 10 minus 2c equals 0, you can solve for C. You bring the 10 over to the other side of the equation, you can divide by them with -2. You end up with a C is equal to 5 as your solution. For the second one, you can solve for Q. You have 4 minus 2Q equals 0. Again, you can bring the 2Q over to the other side of the equation, divide out by 2, and you should get a Q is equal to 2. So in other words, if there was no budget constraint whatsoever on Carl, It's not that he would eat indefinitely. There's diminishing returns to the point where there actually ends up being negative returns to these goods. And so he would eat 5 coconuts and 2 quail. So even with no budget constraint, you don't consume indefinitely given the setup of his preferences. Now on to part B of this example question number 2. Now we have a budget constraint. We were told that Carl could get up to a total of 5 quail and coconuts, and they were equally hard to get. It wasn't that one had a higher price or cost to get than another one. They were equally hard to get. So what we can do is we can say C plus Q is equal to 5. Basically the price of coconuts multiplied by the quantity of coconuts plus the price of quail multiplied by the quantity of quail has to equal our total income. Our total income is 5, the price of coconuts is 1, the price of quail is 1. So we could set it up that way. We basically could do it a different way, but to keep the prices the same, or the cost of getting each of them the same, it's just easiest to do 1 and 1. You could do a situation where the cost of each of them was 2, but then your budget constraint is different, and you could get 10 total, but then you'd have to reduce it on down. So just the simplest constraint here that we would do would just be to say that the price is 1 and 1, and the total is 5. So if you're doing that, you have your utility function as part of the Lagrangian setup here. So you have the utility function first minus the lambda, or the Lagrangian multiplier, and then in parentheses your budget constraint zeroed out. So you have C plus Q minus 5 would equal 0. Right? So that's what ends up being here. So you have to zero out this budget constraint in order to then plug it into our equation. So step 1, set up your equation with the budget constraint. Your Lagrangian is equal to the utility function minus lambda multiplied by, in parentheses, the budget constraint zeroed out. Step 2, get the first order condition with respect to all 3 of the variables, the first, the second, and then the lambda term. So here we're going to do it first with respect to C. So if you take that utility function, the Lagrangian function actually, with the utility function and the budget constraint in there, and you take the derivative, the partial derivative with respect to C, you should get an answer of 10 minus 2C minus lambda. If you do it with respect to Q, you should get 4 minus 2Q minus lambda. And then if you do it with respect to lambda, you should get a 5 minus Q minus C. Again, make sure you can do this math. Work through it when you're doing your example problems, and make sure you can do this part of it as well as understand when I am doing it on here. You should be able to do this math for yourself, and if you have problems with it, again, check online to make sure you can do your derivatives, check with other students, check in the book, and check with me if you don't know how to do the math. Now in this example, we're on to step 3, solve each variable for the lambda term. So we had 10 minus 2c minus lambda. Again, zero that out, that's equal to 0. Solve it for the lambda term. Here it's pretty easy. 10 minus 2c equals lambda. And then our other variable that we were dealing with, we can do 4 minus 2q minus lambda. Again, that should be equal to 0. And so what you can do is then just move the lambda over, and you get this 4 minus 2q equals lambda. So those are our first 2 terms. We don't have to do that for the third term where we took the partial derivative with respect to lambda. We just do it where we took it with respect to q and then with c to end up with what we have here. So now step 4, divide the first variable's first order condition by the second variable's first order condition. So we had 10 minus 2c equals lambda and 4 minus 2q equals lambda. You divide the first one by the second one, and you can get this 10 minus 2c equal to lambda divided by this 4 minus 2q is equal to lambda. These are going to cancel out and equal 1, and then what you could do is just multiply this term over so you can set them equal to each other. Or however the math works for you here from here on out is fine, just as long as you're consistent within the correct rules of math. So here, this is what I've done. I've canceled these out to equal 1, and then I've done 4 minus 2q multiplied by that 1 to move it over to the other side of the equation, so I can end up with 10 minus 2c is equal to that, or sorry, 10 minus 2c is equal to that 4 minus 2q. Alright, so once you've gotten to that stage, then it becomes a little bit easier to reduce, and you can reduce it down to eventually c is equal to 3 plus q. And now I've basically done step 5. I've solved for one of the variables. I've solved for c in this case. C is equal to 3 plus q. So I've gone through steps 4 and step 5. And then now here we're back at step 6, where we take that first order condition of the Lagrangian multiplier, the first order condition with respect to lambda. We bring that equation back in. That was the third of the first order conditions that we took, the third of the partial derivatives that we took. We said from our last step that we had c equal to 3 plus q. What we're going to do is we're going to plug that back into our first order condition with respect to lambda. That we had as a solution 5 minus q minus c. We can set that equal to 0 in this constrained optimization problem. We can zero that out. And what we can do is we can plug this c term, which is 3 plus q, into this equation. And what we end up getting is 0 is equal to 5 minus q minus 3 plus q, as our c is equal to 3 plus q. So then if we want to solve that down, what we can do is we can carry those negatives on through. We can end up with 5 minus q minus 3 minus q. Or you can solve that down, and you can narrow that down even further. And you'll end up with a q is equal to 1 given this setup. And then finally, we get back to step 7. Put your answer back into the first order condition with respect to lambda, the Lagrangian multiplier. So take the solution that you just got from substituting the variable into the first order condition with respect to lambda. That solution of q equals 1. Now plug that into that same first order condition with respect to lambda, that Lagrangian multiplier derivative of 5 minus q minus c equals 0. Plug in this q equals 1 term. So there is going to be a 1, 5 minus 1 minus c. And then you can solve, and you end up with c is equal to 4 in this case. So our solution to this problem, given this utility curve that we have, and the prices and the budget constraint that we were facing, we would be able to say that Carl's utility maximization results in 4 coconuts and 1 quail, given that part B of the problem that we had where we actually had a budget constraint.